about GeoMakie. Just go ahead.
Hi, everyone. Can you all hear me?
Yeah.
Perfect.
Mic's straight, yeah.
All right, so just wanted to give a brief introduction. So Geographic is a data visualization package in Julia. If any of you have used it or heard of it, can you raise your hand? So just so I get an idea. Cool. All right. So GeoMakie is an extension on Geographic to plot geographic visualizations. So what is a geographic visualization? Well, one thing that you could do is you could shade polygons which represent some area, be that a farm, city, country, districts of a country, so on and so forth, right? And so this is just some fake data on all the countries of the world. And you can see that this is actually projected in a map, in a non-square projection. So the idea of this projection is actually to make sure that all areas are the same. So it preserves the area. So the thing is, the Earth is a sphere, right? Well, it's an ellipse, but spherical cow and all that. So because it's an ellipse, you can't really represent it on a square very efficiently. So the idea behind a lot of these projections, which I'll get to in a moment, is to sort of figure out better ways to represent the Earth in a more sort of, in a way that preserves some information that you want to preserve and makes it more perceptually uniform and things like that. So another option that you can visualize is rasterized data. So this is basically values on a grid. And that grid could be uniform. It's usually regular. It could be irregular. There are some examples of that. This is an example of the maximum temperature in the month of, I think this was June. I forgot to label that. But this is the maximum temperature on the Earth in the month of June. This was from the World Climate data set. July, right. So the last aspect of geographic visualizations are projections. So up here, this is a projection which is supposed to keep the area the same. So you'll notice that the US looks a little smaller than you normally see in like a latitude, longitude, rectangle sort of map. Russia looks a little smaller. Africa might look a bit larger, things like that. Up here, this is a really esoteric one. But the idea of this is again to sort of preserve the features of countries, and I'll get to that also in a minute. This down here is the Mercator projection. This is actually a cylindrical projection, so it's as if you projected the sphere onto a cylinder and then unwrapped that cylinder onto a piece of paper, right? The nice thing about this is that it actually preserves your heading. So if I'm pointing in a certain direction and I move to another point, I'll also be pointing in the same direction. This one, for example, would not do that. So as you move on this map, your azimuth and latitude, longitude space would not be the same everywhere. This is a conic projection. So basically, the same way we projected the Earth onto a cylinder and rolled that out, this is projecting the Earth onto a cone and rolling that out onto a flat sheet of paper. And so these all have their own special properties. There are different times when you want to use each. So let's talk about some use cases. So one of the main use cases for polygon-like visualizations is this thing called a choropleth, which I think some people might have heard of. Basically, the idea is I have polygons and I shade them according to some value. This is just an example of India, but you don't have to just have one set of polygons, you can have multiple. So you'll see these darker black lines which indicate state boundaries, and these lighter gray lines inside regions of the same color which indicate district boundaries. So what's being colored is basically a superset of districts but a subset of states. So it's not proprietary, but it's a sort of internal thing called homogeneous regions. The other thing is that, of course, polygons being vector objects, very efficient to project onto all of these projections. You're not doing a grid, you're just doing this one line, so it's easier. So use cases for rasterized data, they're usually values on grids, usually regular. In the Julia ecosystem, they're very accessible. They've become very accessible in the last couple of years thanks to the rasters.jl package, which was written by Rafax on GitHub. A lot of rasterized data also comes from satellite imagery. So, for example, you might have geostationary satellites, non-geostationary satellites. How do you stitch that imagery together? Things like this. But rasterized data doesn't only have to provide images. You can process it into contours, you can make it into a 3D surface, you can do all sorts of stuff. So before we dive into GeoMakie and how it works, I wanted to just go over some Maki basics. So Maki is a plotting package, and there are sort of a couple of foundational concepts that it goes through. One is that any visualization, no matter how complex, will decompose to a core set of what's called atomic plots. So these are like lines, scatter, heat maps, images, surfaces, meshes. And this core set of plot types are the only things which the plotting backends, which would be OpenGL or Cairo, which is a vector drawing library, or WebGL. Now we also have a ray tracing backend, which is especially fun. But these core plotting types are all that these backends know how to plot. Maki does the entire decomposition, sets up all the transformations, tells them, okay, this plot has this transformation to go from its space to pixels and things like this. Now, so a plot is basically something you can draw. The container for plots is called a scene, and the scene encodes basically a bounding box in pixels, so the plots can't go outside of that, and some other things like transformations and things like this. And these sort of, it forms kind of a tree-like structure, which I'll show. So you have scenes which have child scenes, and then plots which are part of that scene, and the child scenes also have their own children and their own plots which are part of that scene. The other thing that Maki has is this thing called layouting. So how do I have multiple scenes, I have multiple axes that I want to show. How do I lay those out on a single figure? And that is done by this sort of grid layout mechanism. The way that we determine that is by putting them in objects called blocks, so an axis would be a block, a little text box would be a block, a slider for interactivity might be a block. But all of those blocks basically just define instructions for which plots to put in a given scene, right? So all the drawing is handled by the scenes, the blocks just handle the layouting. And the other really powerful concept in Maki is that every attribute of a plot, be it the font size, the marker, the color, even the input data, they're all observable. So observables are basically like signals, if you think of reactive programming maybe. But the idea is that I can update these on the fly, and only that value changes. I don't have to completely re-render the entire plot just because I've changed maybe my data points, right? Or the color of my axis is spine or whatever. And this is really useful because when you're creating publication level or just somewhat complex plots, you don't have to go back and re-render the entire thing. You can just change one aspect at a time. So the syntax to change, to set values of observables is this empty square bracket. So that calls set index with just the left-hand side and the right-hand side. There's no actual index value there. And so this attribute is whatever attribute name you want, color, font size, whatever. So this syntax actually allows you to set the input data for a plot also. So I can animate let's say I animate a heat map or a time series that changes over time. I can just keep setting each of the input data points, each of the inputs that the plot receives, I can just keep changing that dynamically. So let's talk about that scene graph for a second, because this will come back later. This is a really simple plot. Basically what you've got is, there's one sort of parent scene. There's this little three-dimensional axis inside. And there's this stream plot, which is basically just lines and arrows, and markers, right? Scatter plot. So this decomposes to a root scene. Another scene, which is this L scene dot block scene. Now, in this case, that doesn't really have anything in there. For other blocks, that would basically have anything that you want to plot in pixel space. So let's say, a box around a little text box, which you don't necessarily need an entire scene machinery for. You can just plot that directly to the canvas. And then the scene itself, which is this sort of layouted scene, which is integrated with the layout system. Inside that, we have two top-level plots. One is this axis 3D, which is those grid lines, some tick labels, things like that. And one is the stream plot. So if we go down a little in the axis 3D, we'll see that one leaf node is this line segments plot, which is atomic. And the reason it's atomic is because there are some optimizations that we can integrate in graphics cards for this. Then there's annotations, which is basically for the tick labels. That decomposes, so what annotations does is it plots a text. What this particular dispatch of text does is it plots another text. What that particular dispatch of text does is it plots one text plot and one line segments plot. The line segments plot is useful mainly when you're doing LaTeX and things like that, so you have the square root that's rendered by line segments, things like that. So does this make sense? I mean, more or less. The other thing that happens here is that each of these objects encodes some transformation. And at any point, if let's say I change the transformation here, that cascades down to all of these. So the transformation could be as simple as scaling the x-axis by 2. It could be as complex as some geographic projection or something like that. So talking about layouts, a couple of years ago, Julius Crumbeagle added a layout system to Maki. Layoutable objects are called blocks. And basically what happens in the internals is that the layout system gives the block a suggested bounding box. The block then says, okay, this is the bounding box you want me to have. This is the bounding box I'm going to report having. So let's say if you've set your axis to have its aspect ratio to be a certain number, right? So that will change what it reports. And then that block tells its own scenes and its own plotting machinery internally, okay, this is the bounding box you have to define on the final canvas, and then that handles all the transformation and all that. Please.
So you say suggested bounding box every once in a while? Does this mean that if someone manually causes a pixel to be drawn outside of that bounding box, will it be rendered or will it not be rendered?
Depends on where you draw it. So if you draw it, so the scene encodes a bounding box.
Mm-hmm.
If it's outside the bounding box of the scene, it's cropped out.
Mm-hmm.
But if you draw anything in a scene whose bounding box is the entire canvas, then it wouldn't be cropped. So that's why that block scene exists actually, is so that you can draw things which are outside the bounding box of the scene. So like all the tick labels, for example.
Yeah.
You must have noticed that in the older versions of Maki, everything was inside the same box. So you couldn't get axis alignment that way.
Yeah, and what is Plus.jl did the same thing, right? Where all the tick labels were manual text annotations added afterwards.
Right.
So yeah.
So a bit of background on GeoMakie. It started out as a small personal project of mine. It was a library to visualize polygons from shapefiles. Shapefiles are basically a pretty standard format by which people ship polygon data and associated values. We quickly added support for projections and a plot recipe geoaxis. So at this point, axes were just plot objects. So like I showed you that axis 3D, that was just a plot in the scene like any other plot. And it had a bit of special handling. You could index with axis to get an axis. But really there was not too much special handling for this. So this was really easy to implement because the scene already had, that scene node already had this geographic transformation encoded. So all we had to do was, sort of sample the tick lines, add a little logic for determining what ticks were where. But it was also kind of inflexible, right? If I wanted to do something fancy, if I wanted to show a singularity in a plot, I couldn't do that. So and it evolved over time, and in its current state, GeoAxis is actually a thin wrapper over the Maki axis type. And it's kind of hacky. Basically what it does is it hijacks some of the plots of the, so it creates an axis. Then it mutates the values of some of the plots of that axis so that they actually form this geographic axis. So in the near future, and there's already a pull request up for this which is being actively worked on, we're going to make a full block implementation of GeoAxis, which makes it a lot more controllable, allows a lot more fancy things to be done, which I'll show. Sorry, how much time do I have?
Start later, you can do 5-10 minutes.
Cool. All right. So, and in the far future, what I'd like to do is have a general nonlinear axis which is capable of supporting arbitrary nonlinear transformations. So there are a lot of fields in which that could be useful. If any of you guys are physicists who look at black holes, or if you've taken a relativity class or something like that, the space near black holes is very warped, right? And to represent that accurately, you need these nonlinear transformations, which currently I think most people just sort of do the transformation on their own, plot it on their own. But if we have tools like this, they would be really useful. And that's not a need that I've seen really filled anywhere. So currently, as I said, GeoAxis hijacks the axis of spines, takes tick labels, all of this. But it lets the axis handle the layout and other considerations. And actually, when you call the GeoAxis function, it returns an axis object. So this is the level of hacking I'm talking about. The pros are that the bounding boxes are tight in input space. Things don't expand past the scene. We don't really need to put that much maintenance into it because a lot of improvements happen on the axis end. We just take advantage of that. The cons, it can't handle cases where the extent of valid lat-long areas is not a box. It's not a rectangular box in lat-long space. So to give you an example, sorry, this is, right. I could not plot this with GeoAxis the way it is now, because if you see this, this is the North Pole. So this is not a straight line in latitude-longitude space at all. It's actually a curve. And as it is right now, GeoAxis could not handle that. So that's the con. So now I'll talk about some of the challenges that I'm currently facing implementing this. And if anyone has ideas, please tell me, because I'm kind of stumped on some of these. The first challenge I faced was how you position the tick labels. So on a normal axis, the X tick labels are offset to the left. The Y tick labels are offset to the bottom. Maybe you flip those, whatever. It was pretty simple. With a nonlinear projection, that offset has to change based on the position of the tick in the projection's input space, right? So for example, if I go back here, yeah, so you can see with this conic projection, right, that some of the ticks are kind of clipping into the axis a little bit, and some of the ticks are really far away from the axis, which is also not that great. So that's one challenge, and I have a somewhat decent solution, so you'll notice that for a lot of the others, they don't clip into the axis, but it needs to be more general. And I'll talk about the solution as well, but on geographic projections, you can't really project points beyond plus minus 90 degree latitude. I mean, it doesn't make sense, right? So what we use is, we use this proj library, which is written in C, and that's been worked on for donkey's years, and it has most of the geographic projections which people find useful implemented. But it doesn't allow you to ask it doesn't allow you to transform a position 181 degrees north and like 20 degrees east or something, because that makes no sense. And mathematically, you can't even put that into the function at some point. So that required some thought, and this is what happens if you don't do that. So this is what happens if I just plot the tick labels where the position is. So you'll see these are all, the center of the tick label is actually the point at which the spine meets the grid line, right? But if we basically try and get the derivative of the transformation, right? The gradient, right? It's two-dimensional, so you can think about the gradient. And I adjust it by that gradient, then I get this, which is slightly better. The issue is that if you try the naive approach of just adjusting horizontally, then some of these would be very far out, and some of these would be, sort of very far in, which is still somewhat the case. I need to refine the method I'm using. You can see down here, for example, they're all like really far out. So that was one challenge. The other challenge, and this was really interesting, is trying to find the border of a projection which is not a box in latitude-longitude space. So let's take again this as an example, right? You can see that the North Pole is here, and this red line, it looks kind of pixelated. It's basically that is the contour of valid to invalid values. So what we do is we actually take the inverse transform. So we have this rectangle in transform space, right? That's pretty much a necessity for any visualization. So we project that back into input space, and we figure out which values are which of those grid points is valid in input space and which is invalid. So this takes a long time to calculate in terms of interactive visualization. It's like 100 milliseconds or something. But when you're scrolling in and out, that's a really long time. So that's what I'm doing currently. But it's a very general method. So if you're just creating a figure which you don't really want to zoom in with, this will work fine. Some future work is to calculate where the grid lines intersect this spine, so that you can find where to put the ticks, so that they're laid out on the outside, people can see them well. So let's take that interrupted good homologous sign as an example. And this time, it's sort of larger. You can see a lot of the stuff. When I apply that approach of transforming from a grid and transformed space back to input space, and I look at the valid and invalid values, yellow is valid, purple. Yellow is valid, purple is invalid. So you can see this contour sort of forms. And if I do the same thing for an orthographic projection, which is what I showed earlier, it's basically the sphere viewed from infinity, then I get this, which makes sense. I mean, it looks like a sphere. It looks like a circle, right? And if I take the contour between these valid and invalid values, what I get is this red line. And I'll just show you a brief video of me trying to interact with it. You can see it's like really slow.
How long does it take to calculate each point?
You mean each
point on the contour how many points on the contour are you doing
I couldn't give you a number because basically it's just so this grid? So this grid is about like 750 by 750 points. So it's a lot. It's a lot. And even
each point's not that expensive.
Each point is not very expensive.
Yeah.
Like these coastlines are actually quite detailed, and they're not expensive at all. But the issue is that if you try and keep one of these computations takes 150 milliseconds on this machine. But when you have a lot of them, it adds up. So talking about sort of future work, if I want to go towards a more general nonlinear axis, what we're doing right now is we're laying the foundations. Ideally, that should support any arbitrary transformation, be able to figure out how to deal with singularities in your coordinate space, have a simple and easy interface to provide information about the transformation. So you could define, a domain. Geographic projections can't go beyond negative 180 to 180, negative 90 to 90. Maybe some weird physics projection doesn't go beyond 2 pi, so you could do that. It would have some uses in physics, looking at space-time, and more generally, any transformation which is not linearly separable into separate x and y components. Because that I can do right now with a standard monkey axis, it's fine. That works. So this is an example of what you can do. Oh, sorry, am I running out?
Finish up.
All right, cool. So this is, I'll just skip this example. This is sort of, this is the space around a black hole. So this is the exterior of the black hole. This line is the event horizon. This is within the black hole. That's the singularity. And this is sort of plotting the course of an object as it goes towards the black hole. This is an attempt to do it in Maki, which I keep revising as time goes on. Some cool examples. So this is an animation of the precipitation in the world over a year, on average, from the world slime data set again. And the code for this is actually just this. It's really simple. So we download this raster series across time here, which is really simple thanks to that rasters.jl package. Data interpolations. So this is an interpolation package which basically just works with this random array type which it doesn't even know about, which is really cool. This creates a heat map. This creates a color bar. And this little record statement, what it's doing is at every time step, which is defined by this linear range, it's updating the title, and it's updating the input argument of the heat map by this interpolated value. So it's really simple to do this kind of stuff in Marquee. This is a surface of a similar thing. So you can plot a raster as a surface, no big deal. I'll skip this. This was really cool. So this is a poster made using Marquee entirely. The idea was both to create a nice layout, and this data over here is fake. This is actual precipitation data. But you've got this really nice layout. You've got the legends down here, little QR code which you can scan, large margins so you can frame it. This is just an example of the kind of things you can do with Marquee in general. So yeah, thank you everyone.
Thank you very much. Do we have any questions?
I guess sort of a data format question, so this is sort of outside of scope, let me know. What is your support for things like guild text, like non-traditional representations of geographic data?
I'll put it this way, if you can get it into Julia, you can probably plot it. So GeoMakie doesn't really deal with file handling. So the idea is the user deals with the file handling, you give us a polygon-like object which satisfies this package called GeoInterface. And then from there we can consume that and plot it.
More questions? I have a question.
Oh, sorry.
I can take your question.
How do you handle interrupted polygons? Some map projections, like Google sign, that probably non-linear
Right.
transmission, would really should require you to take a polygon and then cut it in half.
Absolutely. So that's something that we're not handling yet, but we're planning to handle that actually at the backend level. So the backend is what does the transformation. As it's performing that transformation, the idea is that it should know, okay, I have to cut this here, restart it here. So we can provide an interface for that.
More questions? I think we'll take the break. People can get first serving of pizza when next speaker sets up. And we'll thank, sorry, I forgot your name.